Good afternoon and good morning for the people from the West Coast. We will now move from the Alaska subduction zone to the South America subduction zone, in particular, central Chile. So, here the map in the Pacific, we have the Nazca Plate subducting beneath the continental South American plate. And the most populated city is the capital, Santiago, which is about 100 kilometers east from Valparaiso, which is the main harbor, the main port in Chile. In Chile, in the central Chile, approximately 8 million people is the population, 8 to 9 million people. So in terms of seismic and volcanic seismic hazard, it's very important the understanding and the research in this area. So here in Santiago and Valparaiso, we have the trench and a hotspot track, the Juan Fernández Ridge, which the hotspot mantle plume is located 900 kilometers to the west and the Robinson Crusoe Island, near the Robinson Crusoe Island. And this is the closest seamount group, the O'Higgins seamount, which is the next seamount close to subduction or collision with the South American plate. Magnetic anomalies show already a subduction of a seamount of similar size of the O'Higgins seamount, which is called the Papudo seamount in this area near the trench. So the Juan Fernández Ridge has an important implication in the tectonic configuration of the margin. For instance, here we can see a map view from the west to the continent. Here's the seamount. And you can see here the trench, which is, you can see very well-pronounced, well-developed auto-risement and faults, and a sedimentation, dramatic change from the north to the south. Here you can see a flooded sediment trench field of turbidite. This is recall that south of Chile is the weather is more like Mediterranean to glacier to the south, like Alaska, like Cascadia, but in the north of central Chile it's a desert. It's very arid, and there is no much sediment supply to the trench because of desertic conditions, and the trench is poorly sedimented. And also the Juan Fernández Ridge behaves as a barrier because the oceanic place becomes older to the north, so the sediments move northward, but they are blocked, dampened by the location of the Juan Fernández Ridge of the seamounts. So seismic studies show that North Chile is more like a subduction erosion margin, but south of Juan Fernández is, in the last 3 to 4 million years, is a accretionary margin. Also, please note this San Antonio Canyon, which is a continuation of a river, the Maipo River, and the zigzag shape reveals that this morphology is produced of tectonic activity. So I wanted to show you active seismic results. So in particular, 5 profiles using wide-angle seismic data: profile A, B, profile 2 and 1, and profile C. This is the Juan Fernández Ridge collision zone, central Chile. And this is the post-collision zones. I'm going to show you an animation, how was the collision of the seamount track with the continent during the last 60 million years old. So a student used paleo kinematic modeling using magnetic anomalies and chemical ages of seamounts to constrain this model. So you can see the video, right? Yeah, so the Juan Fernández Ridge is the orange curve. So the first collision was here in the north of Chile, 25 and then migrate southward very quick. So what was somewhat quick, the video. But here was the first collision, then moved to the north, then remains stationary, and then migrates southward up to the last 10 million years, and has been stationary during the last 10 million years here in central Chile. So it remains in the same area approximately during the last 10 to 15 million years. So the last animation you can also summarize it here. So the first collision, well, the 15 million years ago collision was here in the north, then migrates to the south very quick, up to the current position, and then remain stationary in a band of about 1 degree between 33 and 32. So we can say the collision is stationary here. So some people make a link of this stationary collision with the formation of this huge forward basin. This is the Valparaiso forward basin. You can see here an scarp and the epicenter of this forward basin. The thickness of this forward basin is about 3 kilometers. Yeah. So I'm going to show you the results of profile A, B, C, A, B, 2, 1, and C. These are legacy data that were acquired using the Sonne Cruise, the German vessel, in 1995, so already 31 years old. And still we can do a lot of improving with new techniques. Yeah. So also before the trigger results, the profile A and B are in the post-collision zone. Profile 2 and 1 are in the current collision zone since 13 million years old until the present. And profile 1 is a bit south of the collision zone, and profile C is more than 100 kilometers south of the collision zone. Also, seismological data, natural seismology shows here the hypocenters in the area. And you can see here the track of the Juan Fernández Ridge according to this paleokinematics models. And you can follow the track. This is a very interesting feature. You can follow the track even in the back arc in Argentina here. Of course, this is intra-slab or intermediate depth seismicity. Also, geodetic model using geodesy, locking. This is a locking degree models. You can see here a very very locked area here in central Chile, which is just in this area and the forward basin, and not so far from the trench. Also a locked area here in the south. And the last tsunamigenic earthquake was in 1730. Okay, so almost 3 centuries, and was this the tsunamigenic earthquake. Of course, there are more earthquakes more in the coast, yeah, with a lot of damage in the coast and the continent, but large tsunami earthquakes. The last one was the 1730. So that's why it's so important to study this margin in detail. Okay, so I'm going to use. They asked me to show a slide of the methods. I'm going to use 2 methods: the seismic reflection profiles, which provides constraints from the reflectors of the sea surface below the seafloor. We use a streamer, in our case, of 3 kilometers, with a spacing very dense of geophones or hydrophones, which record or detect the seismic reflected waves, and we can provide a constraint of the reflector of the sediment, and also from the mojo, from the continental base, and any other reflector. Also, we use OBSs, which are started at the seafloor, like ocean bottom seismometers, and they record waves of long wavelength, and they provide very good constraint for the velocity from the P wave, and some cases also the shear wave velocities of the structure. So with these two techniques, we can provide very well constrained for the geometry and high resolution, and also the velocities. So the first profile is in the north, profile A here, 31 degrees south and the post-collision zone, and near the desert, Atacama Desert. And you can see here the trench. There's no mass sediments at the trench. This is a small frontal prism, probably formed by debris. Here is recognizes a very highly active subduction erosion margin. So the horse and gravens and bending faults erode the base and frontal part of a random plate. And there is a waste or short, a waste of the continental crust, which produce some kind of subsidence and reduction of velocities. Here you can see an scarp and a very sharp velocity transition. Probably this is our volcanic rocks, and this is our igneous rocks, part of the coastal cordillera here, which was a paleomagmatic arc in the Mesozoic. And so you can see this contrast and velocities. Okay, this is the profile A. This is the zone of post-collision zone. The Juan Fernández here collide 15 million years ago. Now we move 100 kilometers to the south, and we are approaching to the Valparaiso Basin. And the results are more or less similar. We see here no sediments at the trench. This is the oceanic crust. This is the upper mantle. Here again, the high velocity next to the coastal cordillera, and the middle prism with velocities between 4 and 6, and subsidence here that might be related to subduction erosion of the collision after the damage caused by the Simon's collision. But now we move to the collision zone here in the Valparaiso Basin, profile 2, and it's different. So first we see here for our basin, here we have a lot of sediment for our basin. Probably some studies shows a highly subduction rate and subsidence of this margin, forming this for our basin. Here also we see a kind of paleo basin, but the prominent, the present for our basin is this reflector, and this could be another one. And here we see also the same high velocity zone, which is part of the coastal cordillera here, the mountain range and the coast. There is a small frontal prism, but here we can see already a 1 kilometer thick of sediments at the trench, and horse and graben, and this is the mojo. There is some thickening of the oceanic crust and a reduction of upper mantle velocities. And now we move to profile 1, which is a bit south of Valparaiso Basin. Here we see, you have to take into account this high vertical exaggeration, but believe me, I will show you later, there is a very pronounced horse and graben and faulty normal faults here in the plate. Here we have more sediments. This is the southern part. Here are the turbidites south of the collision zones, and there's more sediments, and the accretionary prism is very well developed. Probably this is also part of the accretionary prism, but the velocity are higher, probably because of more compaction cementation processes. And again, here we see these high velocities and the formation of a low velocity zone, which is very intriguing. The formation, the cause of this low velocity zone. And we will discuss this later. And finally, a comparison of these two profiles, which is in the collision zone. This is just 30 kilometers south of the collision zone. So you can see the difference. This is the collision, and we have less sediments at the trench. Here we have a very well-developed trench basin with a lot of sediments and a more developed accretionary prism. So probably when the Juan Fernández Ridge collide with the continent, destroy or erode the accretionary prism. But in this case, these processes has not occurred yet. And so seismic reflection data provide further constraint, and this is the profile 2 in the central and the collision zones. And here there are less sediments. We can see the décollement, which is the top of the subduction channel. Here we see the interplate boundary, and here the interplate boundary is this reflector, and probably this is the transition from layer upper crust to lower crust, and we can see a lot of thrust faults, inverse fault, which form part of the accreted sediments, and some of those are splay faults from the detachment from the interplate boundary up to the seafloor. Here's a better image. Just assume the resolution is too much, it's too high, so it's hard to show the data in one single slide. But this is assumed, and here you can see the turbidite, the subduction, the décollement, the subduction, the top of the subduction channel, the top of the oceanic basement, and the layer A2B boundary. Here's the accretionary sediment and the splay fault that might arise up to the seafloor, and this has important consequence for tsunami generation. This is the same, but overlapping the model with the BP model with the seismic reflection profiles, the splay fault and several foldings and inverse fault here in the continental slope. The décollement is this reflector, subduction channel, top of the oceanic basement, and here you can already start to see some horse and graben morphology associated to the plate bending. Profile 1, which is south, well, here we have a seismic gap, but the trench field is thick. This is in depth, thicker, and here the Juan Fernández Ridge has not affected the margin, and the accretionary prism is well developed. And also there is the presence of splay faults, and very well developed horse and graben structures in the oceanic plate, in the oceanic crust.
Eduardo, could you please finish in the next minute? You have 1 more minute, possible.
Okay. So this is the profile, this is the profile C, south of the area, and here there's a normal accretionary prism. Higher, very wide, so it's different from the south, it's different from the north. And this is the last slide, this is a comparison of the post-collision zone, the current collision zone, and the south of the collision zone. So here there's the velocities along the plate interface, and this is the plate, the rigidity, and of course they are weaker the rocks, and the frontal part and the shallow domain and the transition domain become stronger up to the Costa Cordillera, and the anomaly is here the profile 1.